Okay. What do you need to be thinking about when you're writing out electron configurations for substances?
The shells. Or the energy levels, rather.
Yeah, shells is the, I'm not a chemist word. That's the biologist word, bad word.
My high school teacher always used the term shells, so it's just like in my head.
Bad word. Get rid of it, scrub it. So what are we looking at?
Sublevels,
And,
orbitals,
and,
levels, and reload.
how about the number of electrons I'm gonna see? So I'm looking at nitrogen and I'm like, the first thing I need to do is I need to place 7 electrons. Okay, so then where do I place them? The first 2 that I'm gonna place are in the first energy level and the only sub-level it has. I have 5 left, so I'll go on to the second energy level, the next sub-level. So now I've got 3 left. Maybe if I could count. Oh yeah, there's 3. Okay, so there's nitrogen. Sometimes you might see this written 1s2, 2s, 2p3, where they don't put the other 2 for the second energy level in. I don't really like that. It's a little bit more confusing, but it doesn't really matter. It's fine. So what do I need for sulfur? Sixteen. All right. 1s2, 2s2, 2p6, 3s2, 3p4. 1, 2, 4. And for iron, how many electrons am I looking at? All right. All right, so remember when you're doing this, that this D comes after this S. And that's probably about it. All right. Hund's rule, what do we have for that?
That's basically that it will fill all of the unoccupied spaces before it doubles up on electrons.
Okay, so inside of a sublevel.
Right. Based off your analogy, it'll fill all the beds in the room before it doubles up.
Okay, so it'll within a sublevel if there are multiple what?
Locations.
Yeah, what's the name of those things?
Orbitals.
If there are multiple orbitals. Um, That make sense? No pairing until each orbital has at least 1 electron. How about the Pauli principle?
You need to have opposites, electrons too,
When?
in the orbital.
So electrons sharing the same orbital must have opposite spin. What's the spin do?
Creates a magnetic field.
Okay, so that spinning creates that magnetic field, and then you've got magnetic fields that are attracted to each other instead of opposing each other when they're opposite. Heisenberg uncertainty principle?
Taking a picture of an atom is impossible. The atom is so small.
Okay.
Atom will always be excited and move before the picture can be taken.
You can never know its exact location.
Every time you look at it, it moves.
You can actually know where it is. You just can't see it. Those are different things. So the actual definition for this is this only applies to atomic sized particles. The technical definition is you can't know a subatomic sized particle's position and momentum at the same time. I could know where it is, but I don't know how fast it's going, and I can know how fast it's going, but I can't know where it is, which basically, the crux of this is looking at it moves it. Why does the shorthand notation for electron configuration have you go to the last noble gas? So
The last orbital level, or the last level of that, before you step to the next row. So it includes everything at that point, and then you add on the last piece.
It's easier.
Yeah, you know it has an octet, so it's just.
no, this one doesn't have an octet.
The last one that will react.
It's definitely about reactivity. So the noble gas electrons are unreactive. And so since we're talking about electrons doing stuff, those electrons are off limits. They just don't do anything. So why bother to even include them? So in lithium, which only has 3 electrons, there's no need to have a discussion about the first 2 electrons. They'll never, ever do anything in a chemical reaction, period. So I could just say helium, and then all those guys are off limits, and then anything that comes after that, that's reactive. And in this case, it's just 1. So if it's something like, I don't know, magnesium, then it's, how many electrons do we have for magnesium? 12. And so the first 10 are neon's electron configuration, and then the next 2 are in the 3s2, and those 2 electrons are very reactive for magnesium. But these first 10 electrons, off limits. These 2 electrons, off limits. That's it. What's the noble gas configuration for titanium? So I find a titanium, 22, back that thing up to argon, and then throw on 4 electrons. So I've got titanium, and then I've got argon, and then 4s2, 3d2. Energy level on for yttrium. Where in the hell is it? Okay. So, 1s2, 2s2, 2p, 6, 3s2, 3. Oh, wait, I'm sorry. We want an energy level diagram, my bad. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 5s, 4d. Whew. 1, 1, 1, 1, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we got 2 electrons, 2, 1, 1, 1, 2, 2, 2, 2, 1, 1, 1, 2, 2, 2, 1, 2, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 1, 2, 1. That's it. So if you added all these things up, they'd add up to 39 electrons. Are we good with that? Which electrons in yttrium are off limits?
The first 36, I guess.
Yeah, none of those are going to react because those are all krypton's electron configuration. So you could only have those 3 electrons that are past that reacting. Okay.